All right, welcome to the Quiz 7 solution video. So this one was on conservation of momentum with friction and just the very brief introduction into momentum that we already have. So no 2D momentum at this time. So for question number 1, we have a child. They are running off of a dock into a boat, and then they are going to move together. Because we are given the child's speed or velocity is 2 and it's positive meters per second, in order for the conservation of momentum to hold true, the sign for our final value is going to need to be the same. So sorry, this doesn't say speed on your version, it says the velocity. So we want to find the velocity in which it's going to be moving away. Again, we have a positive value, so that means that we are not going to be having a negative value for our answer. It explicitly tells us that the boat is going to be moving away, so that is going to be 0. So now we just have to do some math. So we originally have 50 kilograms going 2 meters per second. The child is going to be in the boat afterwards, so that's going to be our 150 kilogram boat plus our 50 kilogram child, and that is going to be the final velocity that we have. And turns out we're going to have 100 divided by 200, which last I checked is 0.5. So our answer is going to be B, 0.5 meters per second. Our second question also has to do with momentum. However, this one focuses on impulse. So if we look at the top here, we have our two situations. We have I and double I, so 1 and 2. So for 1, we have a clay ball coming in, hitting the golf ball, or hitting the bowling ball and moving it upwards. And then the second one, we have a bouncy ball, it hits it and bounces back. So if we think about this, we need to look at the impulse of our object, which is equal to force times the change in time and the change in momentum. So we want to look at the one that is going to have the largest force on the bowling ball. That comes from the largest change in momentum for our object. So in this case, because the bouncy ball has a larger impulse, it has a larger change in momentum, that means that the bowling ball will have to have a larger change in momentum as well. We'll have a larger speed or larger velocity because we do have direction in this case. It'll have a larger velocity and is able to move up further than in situation 1. So larger impulse from the bouncy ball in comparison to, or sorry, the rubber ball in comparison to the clay ball. So they're the same mass, same initial velocity value. It's just how they interact with that bowling ball results in a different force. Our third question is related to conservation of energy. So we have a skier, they are approaching, I guess skis. We have a skier who is approaching a hill, and they're going to be going up the hill. And we are explicitly told that the distance that they are traveling up the hill is 15 meters. And we are being asked to solve for mu in this case. So if we want to compare our points, we'll have 1 and 2. Let's set y is equal to 0 on the ground. So that means that for, we don't have any springs, so I'm just going to completely ignore the last, we know we're going to be able to ignore that. So we have V, X, Y. Do we have thermal energy? So we create our little table. Again, if you are comfortable not creating this table, you don't have to. I know it benefits some students, so I'm going to continue using it. We are moving 11 meters per second at 0.1, and this is our at rest at 0.2, so we're going at 0. We have no elastic potential energy, there's no springs. Based on how we've set up this question, y is going to be equal to 0 at 0.1. We can find the value for y2. y2 is going to be equal to 15 meters, sine of our angle, which is 19 degrees. And when I plug this in, I got 4.8835 meters. So with this is going to be our y value. We need to make sure that we do carry some extra sig figs when doing this, or if you want to leave it to plugging it in till the end, that is fine as well. We don't have any thermal energy at point 1, but we do at point 2. So in order to look at the equation that we have for thermal energy, it's going to be mu times the normal force times the distance that we travel. If we look at the normal force for our skier, the normal force points this way, gravity points straight down, so the normal force is going to be mg cosine theta. And again, we are given the d value, it is our 15 meters. So we are now ready to go through and solve for our conservation of energy. So again, I'm going to be starting by writing the so-called full name for the conservation of energy. I'm going to write out all of my terms, even though I know I don't need all of them. This way I just remember that, hey, in some situations I will have other types of energy. So we can get rid of everything that we don't end up having. So we're going to have 1/2 mv1 squared is equal to mgy2 plus mu mg cosine theta times d. So if you notice in the question, we are not explicitly given the mass of our skier, but by going through and writing out all of the equations that we have, we can see that mass is in every term, so that's going to cancel out. So for rearranging to get mu, I have 1/2 v1 squared minus gy2 divided by gd cosine theta. Here I've just moved the d because otherwise I'm going to forget it when I do my calculation. So I'm going to have 1/2. I was told that my initial speed was 11 meters per second. I'm still on Earth, so g is still 9.8 meters per second squared. I'm going to use the 4.8835 meters for my y2 value, divided by 9.8 meters per second squared, times my distance of 15 meters, times cosine of 19. Going through and assuming I plug this into my calculator correctly, the number makes sense, so I'm guessing I did. I got 0.09095. The coefficient of friction is unitless, so I don't need to worry about any units. And so with this, if I round to the correct number of sig figs, which is 2, my coefficient of kinetic friction on this particular hill is 0.091. So in this question, we have used the conservation of energy with friction, and instead of solving for y2 or d like we normally have in previous questions, we instead were solving for the coefficient of kinetic friction. All right, so that's going to wrap it up for the solution. If you have any questions, let me know.